Okay, in our next example, we're going to look at tunneling IPv6 over IPv4 with Lisp, and it's going to use the same exact logic as we looked at in the previous examples, where we're going to have the endpoint identifier, in this case is going to be an IPv6 address. The routing locator is going to be an IPv4 address, so it's where that service is located. And then the mapping server is going to be running the map server and the map resolver for IPv6 addresses as opposed to for IPv4. So without even having to look at the documentation, if we simply look at what's the format of the config of the map server that we currently have on router 8, in order to change this into an IPv6 config, we would simply say that we are the IPv6 map server, we're the IPv6 map resolver, and then the endpoint identifier prefixes would be the IPv6 formatted addresses as opposed to the IPv4. Now again, this does assume that we have underlying IPv4 infrastructure connectivity from all of the routing locators to the map server, map resolver, and all of the routing locators to each other. Where in this particular case, we were tunneling traffic from router 4's interface and 5's interface over to 3. So we need to be able to ping between all 3 of these interfaces. And then router 6 as the map server and map resolver, we need to be able to ping to that box as well. But the key here is that this needs to be only IPv4. It doesn't have to be native IPv6 transport in the middle of the network. Okay, so also let's look at our IPv6 connectivity on the edge, on the customer edge. So from router 6, if we look at the show IPv6 route, right now we just have our connected interfaces. Okay, we're going to advertise just these loopbacks into Lisp. So on router 6, we're going to do pretty basic config, just IPv6 route, :/0 is via 2001.10.565, which is this guy here. And then also via 10.464, which is via router 4. Okay, so if we show IPv6 route, we basically have 2 static default routes, and we should be doing ECMP between the both of them. Okay, so now router 6 is going to send traffic in both directions. Okay, router 7 is going to send it to 3 that way. So on 7, we'll do the same thing. If we look at the show IPv6 route, we're going to default to 2001.10.373. So we'll say IPv6 route :/0 is via this guy. Okay, from router 5's point of view, if we look at the show IPv6 route, we need to have a return route back to 6. So we'll say that we have an IPv6 route for 2001:6 going to the interface address of 6. And then same thing from 4 back to 6. Okay, so basic infrastructure routing needs to be working first before we think about the core. So if we ping 2001:6, from 4 and 5 we should be able to reach router 6. And then same thing from 3 back to 7. IPv6 route 2001:7/128 is via 2001.10.377. Okay, so now everything within the individual customer sites is working. Next thing we're going to do is to say on the map server and map resolver that we're listening for IPv6 map requests and map registrations, and that we're expecting them for these particular endpoint identifiers. So again, remember with the map server, from a security point of view, it has to manually list the prefixes that it is going to accept. So if we take this configuration for IPv4, we can basically just trade it out pretty much on a one-to-one basis with a v6 variation, which is going to look like this. We'll say that the prefix is going to be 2001:7/128. The other one is going to be 2001:6. And then we are an IPv6 map server and resolver. Now the one's actually doing the registration, which would be 3, 4, and 5. If we show run section Lisp, we're going to say that we are an IPv6 ingress tunnel router, an IPv6 egress tunnel router, and that we're doing resolutions and the requests to router 8 respectively. But the key here is that the control plane information in the core of the network is tunneled over IPv4. So when we do a capture and look at it in the middle, it's going to be v6 in v4, so the devices in the middle don't need to run IPv6 routing. So if it was an MPLS core, then regular LDP is going to work fine. We don't need to do anything like 6PE or 6VPE in order to allow this. It's a transparent connectionless tunnel. Okay, then we're going to do a database mapping that's going towards the IPv6 address. So basically, same thing that we already have here, except that the database mapping now goes to 2001:7/128. And it's mapped to our locator set. So we're saying it's reachable via both ways. Okay, then we are an IPv6 ingress and egress tunnel router. Okay, if we look at the map server and resolver and look at the show Lisp site, we should see that we're registering now our IPv6 addresses. So it says, yes, 10.3.12.3 was the last one who registered that address. If we look at the show Lisp site specifically for the EID 2001:7/128, it says there were 2 registrations, or 2 routing locators, I should say. They're equally reachable via 2's linked to 3 and XR3's linked to 3 with a weighting on a 1-to-1 ratio. Okay, then on router 4, the same thing we're going to do here. So if we show run section Lisp, we're going to resolve this now to IPv6. So the IPv6 tunnel router and ingress and egress tunnel router is us. We're doing a mapping of 2001:6/128, and we're mapping it to multiple interfaces. Okay, so both routers 4 and 5, both of them are going to have this equal config. There's a question here, is dual stack required? No, it's not. So the map server, you could have one map server that's just for v4, one map server that's just for IPv6, or vice versa. And then at the ingress and egress tunnel routers, you can have one that's doing v4, one doing v6, or both combined like we're doing here. They're technically unrelated processes to each other. But really the kind of magic with the protocol that's going on is the v6 EID is being registered to a v4 routing locator, which means you're tunneling IPv6 inside IPv4 when it's going over the core. But within the individual site, yes, you're assuming that you're running dual stack, probably like your servers are running both v6 and v4, or they could even just be running v6 natively. As long as they're going Lisp to Lisp sites, then they'll be able to tunnel the traffic transparently over v4. Okay, so now let's look at on router 8 and look at the show Lisp site for the other loopback. We see that there were 2 tunnel routers that registered it, and they're both saying that they both have 2 routing locators in order to reach there. Okay, so now let's do a ping between them. So let's say in our data plane capture, we're going to look now for ICMP v6. So on router 6, we're going to do a ping to 2001:7 and source it from 2001:6. We should see again, first couple packets are going to get dropped while we're in the middle of doing the resolution. Once the map server says, yes, you know how to get there, I know how to get there, and it's via router 3's interfaces, then router 5 is going to install those forwarding entries. And if we look at the actual pings, which would be like these guys here, okay, here's the echo, we should see that it gets encapsulated inside of Lisp. So it's IPv6 inside of IPv4, and it's UDP. So the outer header is staying the same. It's still 4341 for the UDP port. but the payload is transparently v6, which is being tunneled over the v4 core. So it's a pretty nice solution for this, again, because the tunnels are connectionless. You don't have to run any routing protocols over them. And as long as you don't have a more specific match in the routing table, that's going to cause the edge router to query the map server and map resolver to see, can I reach this particular destination? So like again, if we were to take a look at router 5, who is one of the tunnel routers, and we look at its global IPv4 unicast table, we have the internal routing information that's going like over to router 6, but in order to get to the rest of the public network, we're simply doing just a static route outbound. So we wouldn't need to do any BGP peering in order to do the multi-homing, simply based on the fact that the map server is doing the resolutions for us. We can figure out how to do the ingress-egress load balancing based on those ratios that we configure. And same thing is true with the IPv6, that if we look at the show IPv6 route, the only thing that we have in terms of other than connected routes, in this case, are just a static route to the inside. To the outside, we don't even have a default route configured at all. It's just saying that if you look at the Ceph table and you try to match, let's say 2001::7, and you don't have an entry for this, this is what's causing you to query the map server or resolver. Now, the potential disadvantage of this, though, is that if you send traffic to random destinations, it's going to cause the control plane, it's going to kind of go crazy to say, you know, I'm going to keep resolving all of these over and over and over. Where what I mean by this is on router 5, if we were to debug IPv6 or debug LISP control plane, and then let's say our, I want to say that this would be a map server request, but I'm not 100% sure, so I'll just say all. So if we ping like 2001::8, this should cause router 5 to ask the map server. The map server is going to reply back with what is called a negative match, which is forward native is what it's called. Basically means the map server doesn't know that particular route. So you need to forward it natively over regular IPv4 or IPv6 not Lisp encapsulated. This is how you would go to reach like the regular public internet. But again, the potential problem with this is that if you have tons and tons of destinations that are not connected on Lisp, you're constantly pounding the map server and resolver, asking it for destinations that it doesn't know about. But there is a way in order to customize it to say, hey, I'm only going to try to resolve these specific EIDs if I already know what routes are Lisp aware and what routes are not Lisp aware. And then you would just do either Lisp routing for these and then native routing for the other ones. But again, in terms of the config, it's fairly simple design as compared to something like MPLS Layer 3 VPN, because we don't need to do anything to the core. As long as the core just has basic IPv4 reachability, then all of this stuff is going to be transparent on top of it.